So welcome everyone to the third part of the Gemstone mini course on variations of geometry and the spectrum by Chris Judge. And today we're going to hear about transversality. So Chris, please, the floor is yours.
Right. So thanks again for allowing me to give these set of lectures. It's been lots of fun. Today I want to move into a different topic. It's very different than what I spoke about in the first two lectures in a way, but it also is similar in the sense that those examples I gave about families of two-parameter families of operators, we're sliding, that was sort of a transition into this newer topic. You can think about those results in terms of transversality. But in any case, that for the most part, it's going to seem somewhat different, and I'm not going to make the complete connection. And in fact, in some sense, the connection is not completely developed. There's, on one hand, classical analytic perturbation theory, and then there is this more recent development, transversality, which arose more in the 50s and 60s with the work of René Thom and Arnold and others, and Ralph Abraham, for example. So I want to give the definitions and some examples of transversality. And I want to talk about parametric transversality, which is a major tool in differential topology. And then give Uhlenbeck's application to generic simplicity, and then discuss, there are plenty of other applications, but one of the most recent and striking applications is by Jung and Zeldich, where they prove that you can get three manifolds whose eigenfunctions have exactly two nodal domains. Two nodal domain theorems were known before, but this result is striking because it's basically saying for a sequence of eigenvalues of density 1 in the sense of Weyl's law, you have eigenfunctions with two nodal domains. That was not known before. Okay, so but let's start off with the definitions. Oops. If you have, so the first definition of transverse is the easy one that everyone thinks about. You have two crossing things. Two vector subspaces of a vector space V are said to be transverse if their sum is the entire space. Now, it's not just strictly speaking, the definition includes the possibility that W1 and W2 are both, for example, V, in which case their sum is V. So this doesn't have to be a direct sum. It's just a sum. So it's a little bit more general than you might expect. But that's the definition. Okay, this is the definition that people agreed on. It was very useful. And then you talk about whether maps are transverse. And first we'll start out with linear maps. So I have a map, a linear map from at V prime to V, and I'm assuming that W is in the image. It's a subspace of the image. And I say that F is transverse to W if F of V prime and W are transverse. If those two, the image of V prime. So I'm replacing W1 with F of V prime, and I'm replacing W2 with W. But then that's the same as just saying that F of V prime plus W is equal to V. So you can achieve all of V by looking at the image of V prime plus this other subspace of the image of the co-range, whatever. So then I have the notion for a differentiable manifold, and just like in anything in differential topology, you start out with some notions in vector spaces, and you generalize it to maps and spaces that approximate Euclidean space, some vector space. And so the way it goes here is if you have, so we suppose we have the first version is we have a differentiable manifold. We have two submanifolds. We're going to assume that those two submanifolds are nice and differentiable. And we say those two submanifolds are transverse if the tangent space, if you have a point of intersection between these two things, y1 and y2, then the tangent space at the of y1 at that intersection point and the tangent space of y2 at that intersection point makes up the entire tangent space of x. So here I have two curves, and together they make up, their tangent spaces together span R2. And then similarly, I can extend this to the notion of map. So we say that F is F is transverse to Y, oops, I should say Z. Got this backwards. Right, I did some. Yep, that's a typo. Transverse to Z. If the image of that is the image of the differential, that is the image of the tangent space plus the tangent space to Z is, so here's tangent space to Z, here's the image of the tangent space, image of the tangent space under the map F, the differential of the map F, and together these two vectors span the entire tangent space. Okay, any questions about the definitions? Okay, so this is a basic course in differential topology. Would of course cover this, but I'm not assuming much in this lecture. Okay, so for basic examples, you have two curves, C1 and C2, and these two curves are transverse. They sort of meet transversely. And an example of a map is, instead of thinking about curves, you think about one fixed curve, and then you think about paths. So a path for me is actually a map from the interval. Its image is a curve, but this would be saying that alpha is transverse to C. Okay. And of course, the example of not being transverse is if they're, the prototypical example is where they're actually tangent. So here the tangents, this direction is, at this particular point, this direction is not spanned by the union, by these direct sum of the, or by the sum of those tangent spaces. So I'm missing this direction. So it's not transverse. And of course, there's a little bit more flexibility using the map definition, because you can have an intersection that sort of looks like this, and it's transverse at each of the pre-image points. So there's a point where it first passes through the point. There's a second point. So it's a little different than just saying that the submanifolds themselves are transverse. So it's, you know, and it became clear in the development of the theory that this notion of having a map being transverse was important. Okay, so one important remark is transversality is stable under perturbation. So we want to perturb things because we're going to take eigenvalues, eigenfunctions, perturb the operator, see what happens. And transversality is something that's stable. That is, here it's not stable, of course, because if I can take these two curves and make a perturbation, and they no longer will be intersecting. But if I start with two things that are transverse like that, then after a small perturbation, they'll still be transverse. Okay, so here's a problem, and I want everyone to participate, so put on your thinking cap. And suppose we have an open set in R2, so omega. It's simply connected, a convex if you like. And I have some curve, maybe the nodal set of some second Neumann eigenfunction, one of my favorite eigenfunctions. And this curve divides the omega. If I take away the curve, it divides it into two components. And then I have 2 points, one point which is in one of the components, and I have another point that's in the other component. And then the question is there a C1 path alpha from x plus to x minus so that alpha is transverse to that curve C? Okay, so now I'm going to wait. I'm not muted anymore. I mean, I can hear you now, but so I'll wait for the answer. Oh, Carlos has.
I mean, it would be surprising if the answer was no.
Well, the answer is yes. Good. Okay, so we got to a good thing. The answer is yes. So how? How? And so there's a typo in the definition of 2 prime. Oh, did I make a typo up here? What should I be writing? DF. Oh, this should be x prime. Thank you. Yes, yes, yes. This should be an x prime. Yeah. Thanks, Rick. Okay. Okay, so but I'm looking for in the chat Jordan curve. Okay, that's a good thing. We're brainstorming at this point. Brainstorming is good. I mean, what's the most obvious?
Curve, so you take a straight line between the two and then you just perturb the curves, then would it not become transverse?
So the nice thing to do is to draw a straight line between them. Absolutely, absolutely. Let's just draw a straight line. Okay, but of course there's a problem with this because the curve C might actually do something like this. And so although it may be transverse here, it's not transverse there. And we don't, I mean, like it's a nodal set of an eigenfunction. We don't know what the actual curve is. So how would you fix that?
Wiggle it a bit.
Wiggle. Okay. Perturb. Local perturbation. Excellent. Okay. Yeah, exactly. So we want to perturb, but we have to perturb correctly because if it could be that if we perturb a little bit, just wiggle that curve a little bit, it could have been that the actual curve, maybe the actual C was actually tangent there. In which case, so maybe that's a bad perturbation. So the answer to this is you have to look at all perturbations and show that the generic perturbation is good. So, and that's sort of that's how Uhlenbeck's theorem works. Okay, so in this particular case, so perturb is the right answer, or wiggle, and it's a sort of an obvious thing. By the way, it's sort of actually an important thing if you're doing like geometric intersection number in topology, or even algebraic intersection number, and you want to make sure you can compute these things reasonably. You have to have things that are transverse to talk about the intersections, count intersections properly. Okay, so so here's the parametric transversality theorem, which is sort of the theorem that makes everything nice. So what we do is we have a space X, so we have a parameter space B. So B is now, we're going to perturb, and B is going to represent the parameters by which we perturb. And I take the Cartesian product of those two spaces, and I have the image space Y. And the basic theorem, parametric transversality theorem, I mean, some people, I've seen, Uhlenbeck gives a reference to Tom, and it makes sense. And there's also Abraham, Ralph Abraham. It was a long time ago, like 60s or something. So F is going to be, we're assuming F is transverse to W on all of X cross B. And the theorem says if F is transverse to W, so that means that the differential of F applied to the tangent space of X across the tangent space of B, that image is transverse in the usual way to, oh, I shouldn't have said W, I should have said Z. Sorry, today. Okay, Z. This implies that there exists a residual subset. Remember, a residual subset is basically a large set. In particular, in this instance, you can think of it as, if it's a finite dimensional manifolds, et cetera, you can think of it as a set of full measure, a Cornell set. But in general, a residual set is just the intersection of a bunch of dense open sets. So it's large, very large. So this is when I say generic here, today, generic means that there's some residual set. So a very large set, almost everything in B, so that if I take Y, sorry, B, that should be B, gosh, B. If I take B inside that R, so B is in here, then, and I restrict F to the fiber above that B, so pi inverse of B, I restrict it to that fiber, then that's transverse to Z. I don't know why these, it looks like there are these red lines that are appearing on the screen. Is that true? Do you guys see that?
Yeah, I don't,
It's very weird. I don't know why that. Sorry about that. It doesn't show up on my
I
iPad.
think maybe it's one of the participants who used the annotation feature.
no,
So I don't-
no, I checked that, Alexander, it's not the case.
Let me, maybe I should reshare. I'll stop share and reshare. How about that?
Sure, yeah, try that.
Yeah.
Okay, stop share and then reshare. Sorry. It's very weird. Okay. Good. Okay, they're done.
Mhm.
Okay, so okay, so that's the parametric transversality theorem, and it looks very abstract and very unfriendly. But in terms of our original problem, it's actually quite concrete. So in our original problem, the x is going to be the arc length for the curve, or the length parameter for the curve, or for the path. Y is going to be our open set. Z is going to be our C, and we're going to define f of tb. So B is going to be I think an interval would do. So I can take B, capital B will be some interval. And what I'm going to do is look at all these, this family of maps. It should be alpha B of t. Alpha B. So this, I'm going to look at all these. So these are curves that join x plus and x minus. And if I use an interval, I can make parameterize these. If you're by this parameter b. Okay, and so I get this collection of curves that gives me a map from. So that's going to be the alpha b of t, and the map f is going to say take an x, which is -1, 1, cross b, which is I'm going to take to be an interval, and it takes it into omega. And if I define these things correctly, nicely, then the differential is going to be surjective, except at maybe the endpoints. At the endpoints, there's an issue, but otherwise, I have sort of this complete family of curves. Right. So I've added in by adding in the parameter b. I now have, when I take the derivative, I have this new direction that I get in the image. So this map will now be, the capital F will be surjective. And in particular, it'll be transverse to C, because that's okay. I mean, if it's surjective onto the tangent space, then it doesn't matter what C is, actually. It's vacuously transverse to C. Okay. And then the parametric transversality theorem says that there exists a residual set of the parameters B, so that the restriction to a particular B some alpha b, in fact, a residual set of them, a lot of them, are going to be transverse to C. So it's the usual problem. You're always looking for something, and you know it's always there, but every example you look at is bad, right? And this thing tells you that you actually, in fact, everything is good. So any questions about that? Okay, so now, in fact, one way to think about this theorem to bring things down, in fact, this is the level at which Uhlenbeck's simplicity result is proven, is to think about a simpler case where you're only interested in regular values. So let's just suppose we have a map from X to Y. It's X and Y are manifolds. F of X is a regular value if and only if the differential is surjective at each preimage. So that means that if I look for each X that's in F inverse of F of X. So F of X is one particular value, but there are many other things that have that same, that give that same value, and that's this level set. So for each thing in the level set is corresponding to that value, I want the differential to be surjective. But if you check what the definition of transversal means, that means F is transverse to the point Y. Y is equal to F of X. Okay, so it's a very nice simple case. Instead of having this complicated Z before, which what would have been that curve, Z was a curve. Now I'm just taking Z to be a point. It's a zero-dimensional manifold. Okay, and then the reason, so why is this this special case an important special case is because if you know that Y is a regular value, then the inverse image of Y is a submanifold of X. In some ways, this is just a fancy way of putting together the implicit function theorem. The implicit function theorem does things in local coordinates, but if you think about it, but this statement is really local. It's completely local. So this is just a different way of packaging the implicit function theorem. And so what we're saying is that we have this level set, and this is a submanifold. In implicit function theorem, we just need to check that the differential in this direction is surjective, but it is because the whole thing is surjective. Okay. So the tangent space, of course, by the way, to this curve, we all know that if you take a level set, and then the tangent space is actually the kernel of the differential. Yeah. Okay. So that's the implicit function. So the notion of regular value goes hand in hand with implicit function theorem. Okay, so now for this special case, let's look at the corollary of the parametric transversality theorem. In this particular case where Z, that submanifold, is just a point Y. So I have a map from X cross B to Y, and then I have a point Y inside Y. That's my zero-dimensional manifold. And so saying something is a regular value is essentially the saying that this map, capital F, is transverse to this point Y. It's the same thing. So having a regular value of F, well, the parametric transversality theorem would say that the restriction to each fiber is transverse, but again, we're looking at a point, Z is a point Y now, and so parametric transversality theorem restricted to this regular value case says that there's a residual set, though, so that for every B, the restriction of F to the fiber is transverse, and so Y is a regular value. Okay, so that's just restatement within this special case. Okay, but one of the reasons I like this because it gives this picture. There's a picture of how to think about this theorem. So I have this map F from x cross b to y, and here I've written b and x. And F inverse of y, well, it is because y is a regular value, F inverse y is a submanifold. So I have this submanifold. But then there are places where things can go bad, where things can go wrong. In particular, when I have a fiber that's sort of tangent at this point. There, at that particular point, I might not be able to apply the inverse or the implicit function theorem to the restriction. I might not be able to see regularity. I might not be able to use regularity there. So and here also, and here, there as well. But away from those points, everything is good. Away from those points. So these are the exceptional points. But for a residual set, everything is nice. Okay, of course, this is a one-dimensional, the fibers are one-dimensional here, so it's not easy to see visually, but this is the cartoon that I wanted to emphasize. And then, yeah. Okay, any questions about that? Okay. So now let's move into Uhlenbeck's application. So now V is a vector space, and we're going to assume that we have, let's just start without doing any parameters, just like we did in the beginning without having any parameters. Now we have a linear map from a vector space to a vector space, and I'm assuming it's a symmetric matrix, or if you like, a self-adjoint operator. In the self-adjoint operator case, I'm not going to get too much analysis, is that really, if it's a differential operator, for example, I'll have to actually choose V prime to be densely defined. It might be some Sobolev space inside a larger Sobolev space V. But okay, let's not worry about those details. So let's just, if you like, just think about matrices, symmetric matrices. And we're going to define Uhlenbeck basically defines a map F. And what we do is we take away 0 because we don't like 0. She takes the sphere in the vector space, but it's not necessary. You can just take away 0 and then use homogeneity properties. So you take that space. Oh, shoot. Oh, the wrong thing again. Okay. And then you cross it with R. R is going to represent eigenvalues, and you define f of u lambda to be AU minus lambda u. And that, of course, that's the thing we were interested in. And in particular, we're interested when that can be 0. Okay? By the way, this is a nonlinear map. It's not. It's a differentiable map because lambda times u, that's not linear itself. So there's eigenvalue problem is a nonlinear problem. Okay, so Uhlenbeck's theorem says if 0 is a regular value of f, or this is, sorry, it's not a theorem, this is a proposition. I think it's proposition 2.4 in her paper. 0 is a regular value of f. Maybe I should just say implies that the dimension of, that's probably too, I shouldn't say if and only if. If 0 is a regular value of f, then the dimension of the kernel is less than or equal to 1. Of course, what does it mean by the dimension of the kernel is actually equal to 0? It means that lambda is not an eigenvalue. It's either an eigenvalue or it's not an eigenvalue, and if it's an eigenvalue, it's simple. Okay, so being a regular value for f is gives you this. Okay, so let's go through the proof. The proof is very simple. Suppose you do have a point on your level set, a u comma lambda on your level set, then u is in the kernel by definition, and it's non-zero because I've chosen this part. That's why I chose the 0, get rid of 0. And then I differentiate. So I apply the product rule, and the product rule gives me the differential looks like this. So here is the vector at which the vectors I'm differentiating in the direction of. I'm direction of b mu, and this is the point, the base point. Okay. And by hypothesis, 0 as a regular value says that the image of the differential at that point is going to be all of V. That's hypothesis. On the other hand, from this calculation, I know that since I'm allowed to choose any V and any mu, I get the image of A minus lambda I plus the span of U. So this is the span of U. But
Sorry,
I
Chris,
know that, oh, sure.
there's a question in the chat asking if, so lambda is the eigenvalue here, right?
Right. So once I know that that this is true, then U is an eigenvector and the eigenvalue is 0 with eigenvalue lambda. Gosh. Sorry. Okay. Thank you, Cortan. Okay. So but because A is symmetric, I know that the image doesn't intersect the kernel. Okay. Because the kernel is orthogonal to the orthogonal complement of the image, and yeah. Anyway, so it's this trivial intersection for asymmetric. Okay, and then that means that this is a direct sum. That this up here is a direct sum, and in particular, it also means that this U spans the entire kernel. So it is the kernel, and therefore the kernel is one-dimensional. Okay, so we can characterize simplicity in terms of regular values for this function, and so then the parametric transversality theorem says, okay, well, maybe for a particular A, this is not going to be simple, but if I take a family of A's, then I have a chance. In fact, I should see a residual set, and that's basically, this is a cartoon of Uhlenbeck's theorem. We set this map f of v lambda b to be ab minus lambda I. So now I'm allowing for parameters b, and if 0 is, so we have 0 as a regular value of f. Suppose we know that, that's a hypothesis for this theorem, then it says that the parametric transversality theorem says there's a residual set of R and B such that we have 0 as a regular value of AB, but we saw above that's the same as saying that it has simple spectrum. And so this is from the proposition. Okay, so this is the basic use of parametric transversality for the simplicity result. Any questions about that so far? Okay. Now let's look at an example. So what the game is now, we need to fulfill this hypothesis. And it's not easy to fulfill. So I mean, it's not going to work in every situation. You have to have a particular family of operators. If your family of operators is too small, that is B, the dimension of B is too small, it's very likely that you'll have no idea how to use this. So it's important in Uhlenbeck's example, this is one of her primary examples, is she takes Laplacians on a compact manifold. Let's suppose there's no boundary. You can do things with boundary, but let's suppose that. And let's look at all CL metrics. So L is some number, maybe 2 or something. Look at B as all the Riemannian metrics on your compact manifold. And you want to use V to be some sublet space. Of course, again, you might want to think about a V prime in your domain where V prime is equal to like HK minus 2, or HK, sorry, plus 2. HK plus 2. I'm going to add some regularity on your domain space, but that doesn't, I should also say that you need your map F to be, in that case, you need your map F to be Fredholm. So this whole game you can play with transversality works very well if you have Fredholm maps, which Fredholm maps between Banach manifolds are simply maps, which when you linearize them at the tangent space, they become Fredholm linear maps. And so, okay, I'm avoiding all the Fredholm issues, but it's Fredholm is exactly the right category to be thinking about. And in fact, the proof of the parametric transversality theorem requires a version of Sard's theorem, and there's a Smale provided a version of Sard's theorem that allows you to work in Banach spaces. So, right. So let's look at now. This is the Laplacian, our favorite friend, and we're going to use f of u lambda b is to be this. So now it has three parameters. These were from the original application to a single b, and then now we add on the parameter. So now we have three things. And the theorem of Uhlenbeck is that in this situation, 0 is a regular value, and therefore I can get simple spectrum generically. And the proof idea is simply this. Suppose, or the beginning of the proof, I mean, there's more, I'm just going to give the beginning. Suppose we do have a point on our 0 level set, and let's look at the differential. Well, we compute the differential just as before using the product rule. And this is what we had before when we didn't have a b. The new thing is this part. That's the new b part. We have to differentiate delta b in the direction c. C is sort of the direction in which you're perturbing your Riemannian metric. And then oftentimes this, instead of writing all this mess, people write just delta dot. And here I'm writing delta dot c to indicate that I'm actually differentiating in the direction of c. So I'm changing my Riemannian metric in the direction of c. So c is some tensor, a symmetric tensor. The tangent space of Riemannian metrics is very nice. I mean, the space of Riemannian metrics is sort of like a cone inside 0, 2 tensors, symmetric 0, 2 tensors. And so it's very nice Banach space. And so we can talk about tangent space to that space. And then the game is to prove that delta dot c times u, that is all the things here, are dense in V. And so in some sense, you ignore this part. This part is too hard to understand. By adding in the B part, you've added enough. It's not the whole thing. You show it's dense, and then you can pick up a little bit more by using sort of Fredholmness and this part. But the main part is to show that this is very large. And to do that, she basically looks at conformal deformations and also volume preserving deformations. And the game is to show that if you have, say, delta Cu, if you want to show that's dense, well, you suppose not. That is, you suppose there is some function V, which is in your V, so that when you integrate it over your manifold, you always get 0 for all V, and you get a contradiction. Or in other words, if you don't like it that way, this should imply that V is equal to 0. And if you do conformal deformations, you can sort of show that this is somewhat like rho times UV, rho times the Laplacian UV. So the delta dot is like rho times the Laplacian, where rho is your conformal, is the derivative of your conformal deformation. And then that's the same as rho. Right. What I should say is, I should have said this, for all the implies delta dot to u is equal to 0, which it's not, right? So I should think about this by contradiction. Gosh, yeah. So I suppose that this is equal to 0 for all v, and I get a contradiction. Let's think of it that way. So delta dot is rho times delta u, so times v, that's 0, so that's the same as rho times lambda times u times v is equal to 0, which is the same as rho, for all c, I should say, for all c. That's what I would say. That's the same as saying lambda times rho u times v is equal to 0. And rho is arbitrary. And u doesn't vanish except on a very small set. It doesn't, and so this will imply that v has to be equal to 0. Sorry, I kind of forgot which I was trying to do. So that's for the conformal part. That gives you enough deformations in one direction. There's you also need to use the volume preserving things, volume preserving deformations. Okay. Yeah, any question? I imagine I generated lots of questions, maybe not. Okay. Okay. But what I do want to emphasize is that it's necessary to prove that you have enough deformations. You have to have enough, this space has to be large enough so that when you look at all the possible perturbations of your Laplacian, that set will be dense in V. So you have to have lots of perturbation. You can't expect to do this if B is finite dimensional. You you shouldn't hope to do it if B is finite dimensional.
Well, there is a question in the chat asking if you're using that variations are sums of conformal and volume preserving ones.
I mean, it's true, but I mean, if I can get away with just using the conformal deformations, that would be good. But you actually need to do more. You need to use volume preserving ones as well. But I just need to know that there are enough. I don't need to use all of them. I just need to know that B is large enough to produce enough variations in my operator, so that when I fix this u is fixed, by the way. This u, I'm fixing u, and then I have to, the way I generate new stuff is by doing this. So I have to make sure that even for a fixed u, I can use enough variations C so that this set is large. And maybe you just need conformal deformations. Maybe you just need volume preserving deformations. In this case, Uhlenbeck's proof uses both. I mean, there's a different way of doing it where you just don't even worry about whether they're volume preserving or conformal. You kind of just do all the deformations at once. Anyway, but this is how she did it. So anyway, but this is the trick. You have to know that you have enough deformations to generate that this is dense. Okay, so that's yeah.
Sorry, why did you only need to show like one of the terms has a dense image? But
Right,
like
because,
df is the sum of three things.
Yeah, so I just need to because if I want to show that the image is dense, I just need to know. So what I'm going to do is send. So basically, when I can, well, okay. You're asking about why I only need to have it dense, or why I don't have to worry about this part.
Right. Why don't you have to worry about that part?
I mean, in some sense, I do, because dense is in some sense not enough. There's an additional argument that involves messing with this part, but let's suppose that that's not an issue. Then I'm just taking I just need to show that this set, I need to show that the image, take all these things and show that I can get as close as I want to something in V. V is on the other side. And it's enough to show that I can get close with anything that looks like that. So it can take mu equals 0, that's 0, and V equals, no, so I did it backwards. I'm really sorry. I must be too tired. So 0, 0, C. Sorry. Yeah. So I can set V equals 0 and mu equals 0. And then I vary C. And so if I can, so that means that this part's out. And if I can show that I can get close to any point in V with a 0, 0, C, then the image of this thing is dense, right? So if I have one map from X to Y, and I want to show that f of X is dense, then I only need to show that if I take a subset, I only need to show that f of A is dense for any subset. Suffices. So I'm taking a subset. And the subset are the ones where V and mu are 0. Thank you for the question. Excellent question. Yeah. Okay. Okay. So right. Okay. So yeah. Sorry, I think energy level for some reason stays lower. Great. So yeah. So I'm basically done. I just want to point out that there is this application by Jung and Zeldich, which is just amazing, fantastic. I mean, Steve did amazing work for lots of years, and fortunately, he's no longer with us. But this is one of those nice, beautiful pieces of math he did with Junior Jung. So this was just not so long ago. So here, so I should also say, you're right, wait, okay. So here it's an application where we do more than just the simplicity result. We're going to, they use transversality more than so Uhlenbeck proved not only that the eigenvalues are simple, she also showed that for generically, if you look at the eigenfunctions, they satisfy really nice properties. For example, for the generic B, generic metric or domain, the eigenfunctions will be Morse functions, so that's nice. And also that the level sets will be smooth, and that's used here. And there are other theorems. I think there's A, B, C, D, there's a list of properties.
Chris, sorry, there is another question by Alexander about the previous argument, so in the chat.
This is the HK product in L2. Yes, so yeah, so that's a very important point. Yeah, so this is something I'm sweeping under the rug. You have to be, you want to be dense in HK. Yeah, absolutely. And in this particular application, that's not much of an issue. But normally what we're thinking about is, and this is an important point for her proof, is that we're actually going to use the HK. We're not going to use L2. We're going to use HK. So this is a cartoon using L2 in the product. You have to do this carefully with the HK. So that's a very, yeah, but I'm not going to go into that technical detail. A very good point. Okay. The application again is this. So you have this compact surface. So you start with the compact surface, X, and then we take the unit tangent bundle. So these are the tangent vectors who have length 1 in some metric. It's not important what actually that metric is. You could actually take the projectivization of the tangent bundle if you want. The circle acts, because the circle acts on each, so the tangent space to a surface is a 2-dimensional vector space, and then the unit tangent, the fibers of the unit tangent bundle are circles. And so the circle acts on each of these unit vectors, just, okay? And so you get a, and it's a free action, so you get a free action of S1 on the unit tangent bundle. And then Jung and Zeldich consider the S1 invariant metrics on that unit tangent bundle. This is a compact space, by the way, because the circles are compact and the and the original surface is compact, and locally it looks like a product of circles and a piece of the plane. So this is a compact, the UTX is a compact space. I'm looking at S1 invariant metrics on UTX. And the first thing they use is they prove using methods similar to what we just discussed in Uhlenbeck's original argument, is that the dimension of each eigenspace is at most 2. And it has to be that way, essentially, because you have these this S1 symmetry. S1 acts on the eigenspaces, and it's going to usually act non-trivially. And so you'll get this two-dimensional representations. So they have to be, each eigenspace will be two-dimensional, do that two-dimensional representation come from the S1 action. I mean, S1, you know, the irreducible representations of S1 acting on a vector space are either one-dimensional, trivial, or two-dimensional. Okay, so you definitely will get, and if you just think about it, it's the same reason, the same reason that if you take a circle or a disk and you look at the eigenfunctions for a disk, the eigenfunctions for a disk have a S1 action. It's not free, but it's only has one fixed point, the origin. And we know that the eigenfunctions for the disk are two-dimensional unless you're looking at the invariant eigenfunctions. The invariant eigenfunctions are one-dimensional. Of course, the fact that they're only two-dimensional comes from work of Siegel, but they have to be at least two-dimensional because of representation theory reasons. And for the same reason, this is going to be true unless the eigenfunction itself is invariant under the S1 action. But this only holds for the generic B, just like in the case of Siegel, he proved it for the disk, but in general, it's without some special reason, you wouldn't necessarily expect it to be simple. And Uhlenbeck's theory tells you that this is true. But the bigger Uhlenbeck result, or further results about whether the eigenfunctions are have generically smooth nodal sets, whether the nodal sets are smooth, that can be brought to bear to understand the nodal sets of the Laplacian on these manifolds UTX. By the way, these things are called Kaluza-Klein metrics, and I don't know whether the physicists agree, but anyway, that's what they're called. And using this other theory of Uhlenbeck, they're able to prove that for the generic metric, S1 invariant metric, where U is an eigenfunction, but it's not invariant under S1, then the nodal domains, there are exactly 2 of them, exactly 2 nodal domains. And it is just an amazing result. I mean, there are some classical results due to, I've forgotten who it was due to. Maybe someone will tell me.
Hans Levy and Anthony Stern, yeah.
Right, Stern and Levy, right. So where Stern was working, for example, on the unit square and showed that you could create a sequence of eigenfunctions whose nodal sets divided this square into exactly 2 parts. And back in this is a long time ago, 20s or 30s, and then Stern, Levy later on proved that if you look at the sphere, you could also construct on the sphere nodal sets, nodal eigenfunctions. In both of those cases, you're looking at high multiplicity eigenspaces, and you're just using the fact that if the eigenspace is large enough, you can sort of choose your eigenvector in that eigenspace to have nice properties. But this is a totally different approach. And it's saying also, and it says that not only that there's some sequence, it actually, because the set of eigenfunctions that are invariant is rather small in the sense of Weil's law. It's saying that basically almost all of your eigenfunctions have this property for a generic B. So it's really a totally more enhanced theorem. And I want to end by showing a picture there's an additional idea that gets you the two components, and it comes from a beautiful picture. So let me share that with you. Here's an animation. So this is a toy picture of what that looks like. So what are we looking at? So we're looking at the eigen functions, and actually this is the torus case. I'm looking at X is a torus, and I'm looking at the then I want to look at the unit tangent bundle, and I think of the unit tangent bundle as an interval. Sorry, it's each unit tangent space is a sort of a circle, and what I'm doing here is I'm giving you a cross section that is orthogonal to the circle. So I have this torus, and then I have sort of a circle of directions. I don't think of them as tangent anymore. I just think of them as a product. It's a product. And I'm looking at cross sections. And I'm looking at this is the picture of the level sets of the eigenfunction at each cross section, horizontal cross section. And what's supposed to happen here, and the picture is supposed to show, is that sort of the blue region is as I move through these cross sections, and I have to, it's a circle, so I keep moving back. So there's sort of a repetition, supposed to be a repetition in this picture. The blue set is connected. It's not connected on each slice. On a given slice, the blue set has many different components. But if you now glue all these different slices together, the blue part is connected. So that blue part is sort of where it's positive, and the yellow orangish part is where it has it's another nodal domain. So the blue part is one nodal domain, essentially, and the yellow orangish part is the other nodal domain. But individually, these two different pieces, blue and orange, are connected in the entire 3 manifold. Okay, so anyway, I'm over time. Thank you.
Thank you very much, Chris, for a great talk. Questions or comments? So maybe let me start with a question about Uhlenbeck's theorem. So, am I right that original Uhlenbeck's theorem was stated for differential operators, right?
In her paper, I mean, her paper is she states it she says for differential operators, but she has to give examples. I mean, her paper starts out by talking about, let's start with elliptic operators, a second order self-adjoint elliptic operators, and but then, and then she develops her theory, which is, the transversality stuff. But then to do an application, she only really does 3 applications. One is the application to the metrics on manifolds. The other is to take a Laplacian and add a potential. And the third is to changing the domain, perturbing the domain. But it could be that there are many other situations where you can apply this theorem. I mean, it just have to show this property that the delta dot U, the set of things you generate that way, is dense. Mm-hmm. But her original paper does contain this example. But I think she was trying to intimate that, in fact, this is a very general thing, which it is. But she only gave a couple applications.
I see. Yeah, I mean, I know there is a paper, for instance, about genericity of Steklov spectrum, where it is applied to the Dirichlet-Neumann map, which is pseudo differential. And I mean, I've never really understood the details, but there are some subtleties there. So because the operator is non-local and some other stuff, so that you can apply the same theory, but it's a little bit more subtle.
Oh yeah, no, absolutely. You have. I mean, I mean, it's a wonderful theorem, but it really is difficult to apply, and I would say it's easy to mess up your application as well. And I should have said that one of the two people who have done some really interesting work using this theorem, and they have to justify every time they use it, is Inciso and Peralta Salas.
Right.
They're given, and but you know, you really do have to be careful. I smoothed over all the functional analysis questions, like you know, Alexander was his comment was right on, that there are many analytical issues about checking this condition, making sure that you actually have the requirement.
Okay, thanks. So we have a question in the chat from Alexander. Is this closely connected to the transversality arguments that are used in prescription of eigenvalues by calendar year?
Yeah, that's what I was kind of hinting at the beginning when yeah, so it's a good question that he's more interested. So Arnold also at the same time thought about transversality in term for eigenfunctions and eigenvalues. There's a famous paper, Modes and Quasimodes, in 1972, but the ideas, it's not parametric transversality. Let's put it that way, or at least I don't see how it's parametric transversality. So I think that's what there you are trying to understand moduli spaces of operators, and you are trying to understand how things can be transverse to one another. And so it's a similar, but the Uhlenbeck part is about, you know, generically, can you do something? There, you know, but there, of course, then again, there is a generic part in the Arnold point of view, or what in Colin de Verdier's development of that. And there was also a paper of a student of Lax by Teytel, T-E-Y-T-E-L. And so in that development, it's a little different. I mean, the objectives in some sense are very similar, but the parametric part is a little different. The use of the parametric transversality theorem is different. Yeah.
Thanks. So more questions or comments? So if not, let's thank Chris again for the wonderful mini course.
Thank you so much.
And let me use this occasion to mention that the Spectral Geometry in the Cloud seminar will restart in September. So thanks everyone for participating.
Thanks a lot.
Have a great summer. Thanks a lot, Chris, again.